Today we're going to be talking about improper integrals. And this was a funny meme a few years ago. I'm recording this in the end of October 2020, and this is what we're going to be doing, and it was just a funny meme, so I thought you guys might enjoy that. So for your pleasure, for your humorous math pleasure, whatever. Okay, so our first example here. This is what we're going to be doing. An improper integral is when we have one or both of our limits be infinity. That's one of our types. So what we're going to do is we're going to end up writing that as a limit. And you have to have this limit notation in there. That is super picky. If you don't have the limit notation, I'm going to take off points. You need to have that limit notation. So now we take the antiderivative, just continuing bringing through our limit. We take our antiderivative and we evaluate it. And I have to remember to evaluate it. Minus a negative e to the 0. So now I'm looking at the limit as b goes to infinity of negative e to the negative b plus 1, and that equals 0 plus 1. So that limit equals 1. I kind of have a picture of our area here. So even as I go to infinity, all of this area under my curve is going to go to 1. And you want to recognize that for any improper integral, as long as a is greater than, let me look it up here to make sure that I have it correct. For a is greater than 1, this is going to what we say converge. Converge is a fancy way of saying I can find the integral, I can find a value. Okay, so you're welcome to write this down. I think that it is pretty self-explanatory for us. So if you have your limit value, up here you just write a limit, and you can choose B. Our book chooses B. Another book I've used chose T. You can choose any variable that you want. Okay, so you can do it with a positive infinity, a negative infinity, or if you have infinity, infinity, choose a number in between. I tend to choose 0 to find those, to split up your integral, I should say. So the integral converges. This is a key word. Converges when the limit exists. Otherwise, we diverge. Okay, and then in the third case, the improper integral on the left diverges when either of the, so I diverge when either of the improper integrals on the right, so either one of these two diverge. Okay, so another example for you. And I tried to limit the amount of examples. I tried to pick some good examples for us. So again, you have to write this as the limit as b goes to infinity of 0 to b of x over x squared plus 1 dx. So we kind of expect you to know a lot of these integrals. This is a u substitution where u equals x squared plus 1. So du is equal to 2x dx. So I need a 2 inside, a 1/2 outside, and I can actually pull that 1/2 out even in front of the limit if I want. So now I have 1/2, the limit as b goes to infinity, of 0 to b of 2x, which is our du, over u. So now we have our antiderivative, remembering to keep writing my limits. My antiderivative of that is ln of u. I am not going to put the absolute value signs in because my u is always positive and I'm going with all positive numbers. Evaluated from 0 to b. So now I have 1/2, the limit as b goes to infinity of the ln of b squared plus 1 minus the ln of 1. I plugged in 0. And I'm taking the limit of that whole quantity, moving my work up. The limit as b goes to infinity of ln of b squared plus 1. Well, that's really ln of infinity, and that's really infinity minus 0. So since I got infinity for my limit, this diverges. Okay? I'm going to give us some tests eventually that are going to help us determine whether or not this converges or diverges. Now evaluating this. Again, you can choose a different letter if you don't like B. Sometimes I choose the letter T. Now I picked this example because I really like this example. This is so this integral, just looking at this integral, I'm not even going to put in my integral limits. That's an integration by parts. So u and dv. Remembering to pick my u. Algebraic is the one that I need to pick. So I'm going to pick my u to be 2x. And now I'll explain to you guys why I picked that in a minute. So my du is 2. Well, I didn't carry the negative with it, is what I mean. So then my dv is negative e to the negative x dx. And then when I integrate that, then I have my u substitution, whatever. So it actually makes this integration a lot easier on us. So now my uv, so 2x e to the negative x, ultraviolet, voodoo. So I have I don't know why I'm struggling with this. E to the negative x dx, voodoo. I'm going to put the 2 outside. So now then my antiderivative of this plus c, but really now I can jump here and say that this is 2x e to the negative x plus 2 e to the negative x. I have a 2b e to the negative b plus a 2 e to the b, negative b, minus when I plug in 0, this first term goes to 0. plus e to the 0 is 1, 2. So now finding my limit, I'm going to adjust this a little bit. I'm going to adjust this to 2b over e to the negative b plus 2 over e to the negative b minus 2. So now I take the limit of anything with an e to the b in it. This goes to 0. This one goes to 0. Those should be positive b's. I don't know what I'm thinking. So my answer here is negative 2. So this one converges because I was able to find the actual value. And again, I'll give us a couple tests. This example, none of the tests I'm going to give us are going to tell us right away whether or not we converge or diverge. Okay, now this guy, this one's a beast. This one's beastly for a couple different reasons. The integration is a whole lot of fun, and I have negative infinity to infinity. So we need to come up with a couple values here. We need to split this up into negative infinity to 0 and then 0 to infinity. Now we can adjust and throw in our limits. Okay, so now what I'm going to do, I'm going to add a new blank slide because I'm not going to have room on there. And what I want to go through with you is I want us to go through this integral on this slide. Okay, so this integral, we have to be a little creative. The reason I changed that to x to the third squared is because I see an x squared up there. So then when I do my u, which is x to the third, my du becomes 3x squared. So I need a 3 and a 1/3. So now I have this. So now I have my du over x, not x, Mrs. Marnell, u squared plus 9 du. Now remember that you can memorize the trig table that's in our book. I choose to just memorize how to do this. So I factor out a 9, and that becomes u over 3 squared plus 1 du. So then I have basically another u substitution. I'm going to call it a w substitution since that's our second. I just thought of that. Oh, I'm so funny. First person who laughs at this and writes me a letter will get a prize. It'll be the prize of me knowing that you laughed at me. So I need a 1/3 du. So I'm actually going to bring in this 1/3 in again. Okay. I'm going to take the 1/9 out. The 1/3 gets in, and that becomes my dw over w squared plus 1 dw I already have my dw. We don't want to integrate twice. But I would love you guys to look up double integration for those of you that are really into the math. So this turns into this. Technically plus c. So going back to my previous slide, so both of these turn into this. What was it? It was 1/9 inverse tangent of x to the third over 3, evaluated from a to 0, plus 1/9 limit as b goes to infinity of my inverse tangent x to the third over 3 from, oh, this should be a b up there, 0 to b. Okay, so now from here, I have 1/9, the limit as a goes to infinity, negative infinity, of the inverse tangent of 0 minus the inverse tangent of a to the third over 3. I'm going to pull this 1/9 out, plus the limit as b goes to infinity of my inverse tangent of b to the third over 3 minus inverse tangent of 0. Ooh, that's a lot of math happening there. Okay, so what this all simplifies to is 1/9. This turns into 0. As a goes to negative infinity, inverse tangent is going to a negative pi over 2. As I go to positive infinity, inverse tangent goes to pi over 2 minus 0. So this simplifies to pi over 9. Woo, those were some good problems. And we're only on example 3. Man. Okay, now if your improper integral has infinite discontinuities. So if you have a discontinuity at one of the endpoints, is you just have to, if it's at the upper endpoint, since a is less than b, you want to go to b from numbers a little bit less. Since a is less than b, you're going to numbers a little bit less. If your discontinuity is at the bottom endpoint at a, you're going to a from numbers a little bit more since b is greater than a. If you have a discontinuity in the middle, then you have to split it up and do it like I did before. Again, improper interval converges when the limit exists, and otherwise we diverge. Okay. So let's go through an example. I apologize. This is turning out to be a super long video. Okay. So since if I plug in 4 here, I get 0 on the denominator. So that is an infinite, that is an improper integral. And I have to go to 4 from numbers a little bit less. Since I'm going from 0 to 4, all those numbers are less. So now when I take the antiderivative of that, and I will try and not bore you with this, it turns into a negative 2, 4 minus x to the 1/2 power, evaluated from 0 to b. So now I have negative 2 times the square root of 4 minus b When I plug in 0 there, I get a 4. As I go to numbers a little bit less, this goes to 0. So this whole thing goes to 4. Okay, another example. This is one where I have a discontinuity where I have an asymptote at 4. So I have to split this up into 1 to 4. Okay, whew. Okay, so now I have the limit as b goes to 4 from numbers a little bit less of my 1 to 4. I'm going to write this as x minus 4 to the negative 2, just because it helps me organize. I take my antiderivative. I'm huffing just because I'm worried that this video is too long. So I'm going to apologize in the middle of the video. Well, I evaluate my integral. This is a pretty hefty section, and I wanted to give you guys enough, I wanted to give everyone enough examples so that you understood it. I think it is fairly intuitive. So now, when I evaluate this, so as I plug in numbers a little bit less than 4, I end up going to negative infinity. As I plug in numbers, I don't need my limit because I just evaluated the limit. I'm trying to jump a few steps. When I plug in numbers, I end up with a minus 1/3. When I plug in 1. When I plug in 5, I get a minus 1. When I plug in 4, I get a positive infinity. But to be quite honest, on that last slide, it said that if one of these, if this diverges, the whole thing diverges. From this point right here, I know that that diverges, so the entire thing diverges. Okay? Okay. Now on to these tests that we're going to be talking about. And I call this the p-test. I don't know if that's the technical name for it. It is off of a test that we're going to be doing second semester. But this is really important. And I encourage you to look in the book. The book does this a little bit differently. But if you have an integral that's going from 1 to infinity, or really this can be anything as long as it's greater than 0, of 1 to x over p dx, it converges if p is greater than or equal to 1. We diverge if p is less than or equal to 1. Meaning, if I was looking at this integral, we could say right away that this converges by the p-test. Okay, if it was something like this, we could say that this diverges by the p-test. Okay, so looking at this, determine whether or not this integral converges or diverges. And I'm recording this in 2020 when we're doing our hybrid learning. Normally I would prove that to you guys in class. We'd spend a whole day just proving that in class. I'm choosing not to because my video is already at 25 minutes. But I want to go through a few examples with you guys. We're just going to determine whether this converges or diverges. I'm not going to spend time going through the actual limit. I encourage you to actually find the limit. I'll give you what the answer is at the end. But what I'm looking at here is I'm looking at this integral. and p equals 3, and 3 is greater than 1, therefore we converge by the p-test. And that's important for you guys to state why we're converging. Okay, state what p is, state, and we're converging. Okay, and just so you know, I encourage you to pause the video if you want to go through this. This converges to 1. Our book actually gives us a formula for this, but I think I forgot to, no, I didn't forget to multiply by 2. Our book actually gives us a formula for this. So I encourage you to also read the book and look at the formula. It's not something you need to memorize. It's a pretty easy integral. Last example. Okay. So for what values of p will this converge? Well, we know that the exponent has to be greater than 1. So I solve this. We will converge for p's greater than 4/7. Okay, I apologize for the 26-minute video. Normally in class we'd split this over a few days. Hopefully this was a fairly intuitive lesson for you. And we will go through questions during class.